Hello everyone and welcome to the last lecture of the semester. This isn't going to be a real lecture today. I'm just going to use a few minutes here to review the course material and some of the major takeaways from each of the lectures throughout the semester. And then in the final part of this lecture, I'll talk a little bit about the final exam, what you should expect and how you should approach it. So first we'll just do a quick whirlwind tour of modules 2 through 13 and review the major concepts that we've talked about throughout the course. So in Module 2, we focused on descriptive statistics. We started off by talking about populations and samples from those populations, what the term observation means, and what variables and data sets are. We talked about different data types, so discrete variables that take on categorical levels. These would be described by factors in R. We talked about continuous variables. These are typically represented as numeric variables in R. And then within discrete variables, we talked about nominal variables and ordinal variables. These would be unordered and ordered categorical variables. Okay, our basic descriptive statistics, especially for numeric data, are the minimum and maximum values, and together those describe the range of data. We talked about a few different measures of center, so the mean, the median, and the mode, which again are all the same for a normal distribution. Again, a normal distribution is symmetric about its mean, which means that the mean, median, and mode are all going to be the same. Then we talked about skewed distributions, so positively and negatively skewed distributions, what outliers are, how the term average is used in relation to the mean, and then a few other measures of center were the mid-range. We could do a weighted mean, and we talked about how to calculate a harmonic and a geometric mean, which we actually didn't use too much throughout the course, but it's still good information to know about. We then talked about measures of dispersion, measures of variance in your data. So this can be described by the standard deviation or the standard deviation squared, which is the variance. And then we talked about the standard error a little bit. And again, this is just the error in your estimate of the mean for your data. And then finally, we finished up that lecture talking about descriptive plots that you could use to visualize your data. So we've become very familiar with these over the course of the semester. So scatter plots, X versus Y plots. Okay, time series plots, which is just a scatter plot with time on the X-axis. Histograms, we've built a lot of those over the course of the semester, and density plots, okay, which plot a continuous curve over what you would consider a histogram. We've used box plots quite a lot to summarize distributions of data, but again, remember, you can't really assess normality from a box plot. That's better done with a histogram or a density plot. And then later in the course, we talked about QQ plots, which you can use to assess the normality assumptions for your linear regressions and also look for outliers in your data if they fall outside those 95% confidence intervals on the QQ plot. Okay, Module 3 was mostly focused on data management and techniques we can use in R to read in, manipulate, and output our data. So we talked about different data forms, and there's a lot of different forms data can take in R, so this is always good to review. And again, having the incorrect form of your data in R is a really common source of errors in your code. So when you're trying to run functions on a particular data form for which it's not supported. So these are always good to review and check on. Same with data types. As far as data input, when you read in text files, TXT files, you're typically reading them in with this read.table command. And for this one specifically, remember, you want to specify header equals true because it's not the default for this read table command. We also talked about reading in CSV files, which are a really common way to store your data in a CSV file. And weirdly in R, the default for read.csv is that the header equals true for this function. So you usually don't have to specify that. Okay, just good things to keep in mind in some weird little catechism that's specific to R right here. For data manipulation, we talked about changing the type of data in R using this as.dot command. So as.numeric would change your data to numeric. We talked about subsetting for a couple weeks, as well as merging data by columns. We talked about rbind, so binding by rows, cbind, binding by columns. We can use for loops to manipulate our data fairly efficiently. And although we didn't really talk about these in the course, these if-else statements, a few of you did include these in your code, so these are always good to go review. They won't be on your final exam. But when you use your own code, you may really want to use these if and else statements, these logical statements. While loops are just a different type of loop from the for loop. So check these out on your own time as well if you're interested. These can be really handy. Okay, I use them from time to time in my own code. I actually don't remember if we touched on this repeat function. I'm going to skip that. We did talk about ordering and sorting your data. Finally, once you've finished manipulating your data and you want to output it back into a format that you can send to collaborators. You can use the write.table command to save a txt file, or the write.csv command to save a CSV file. In Module 4, we focused on probability distributions, so some of the properties of these different probability distributions and how they can be applied to ecological data. So we divided these into sort of two general categories: the discrete distributions, so the discrete uniform, the Bernoulli, okay, this is for true, false, or success, failure data, okay, binary data, and then the binomial distribution, which describes a series of Bernoulli trials. The Poisson distribution, again, is a discrete distribution because this is used to describe count data, typically. Okay, that ranges from 0 to positive infinity, but usually these are integer values, okay, discrete. And then we touched on the negative binomial distribution as well. For continuous distributions, we talked about the continuous uniform distribution. Okay, and again, this just predicts that the probability of achieving any number in a given range is equal across all those different numbers. And this is different from the normal distribution, where the probability density is highest around the mean, okay, and then tails off as you move away from the mean in either direction. Okay, so again, the normal distribution is one of the most common distributions that we use in statistics and underlies a lot of the assumptions of the models that we focused on later in the course. So really good to be familiar with the normal distribution. And then the last continuous distribution we touched on in that lecture was the exponential distribution, which can be used to describe time to events, population growth, or decay. Okay, the types of descriptors we can use to summarize these distributions are the probability density function. Okay, and again, this describes the probability of occurrence of different values across that distribution. Okay, when you have a high value for that probability density function, that means that the occurrence of that particular value is very likely compared to a different value that has a lower value on that PDF. Okay, the cumulative distribution function increases as you move from left to right, so it's just summing up the PDF as you move from left to right. Okay, the expectation, that's the mean of the distribution, and then we also have a variance for that distribution. And finally, we have the quantiles. So again, remember that the quantiles are the 0, 25, 50, 75, and 100%. Okay, or those can even be broken up into finer gradations, which would be the percentiles. So the 5th percentile of a distribution is the number at which 5% of the observations occur to the left, okay, are lower than that number, and 95% of the observations are higher than that number for the 5th percentile. The 50th percentile occurs right in the middle, where 50% of the observations are lower and 50% of the observations are higher. So again, that would be the median, is the 50th percentile. And then on the other end, we have the 95th percentile, where 95% of observations are lower than that value and 5% of observations are higher than that value. All right, Module 5, we started talking about the philosophy of science a little bit, and so we touched on the scientific method and then one approach to doing statistics as hypothesis testing. So this is where you're developing a null and then an alternative hypothesis that are mutually exclusive, and then using data to distinguish which one is more likely to be true. We talked about one-sided versus two-sided tests, and then in the context of a t-test or a z-test, we talked about how you can calculate your test statistic, and then from that test statistic generate a p-value, which gives you an indication of how likely it is that the null hypothesis is true given your data. Okay, if it's very unlikely that the null hypothesis is true given your data, then typically you would reject the null hypothesis and side with your alternative hypothesis. We talked a little bit about confidence intervals around your p-value, and then type 1 and type 2 errors in statistics. Okay, good to go back and review those. In this module, we focused primarily on the z-test and the t-test. Okay, these are parametric tests that assume normality. But if your data is not normally distributed, okay, you can use the Wilcoxon rank or the Mann-Whitney U test. Again, these are actually synonyms for one another, but these compare the rank values of observations from two populations, okay, to get some idea of whether it's likely that your two samples came from the same population. And then using this Wilcoxon rank or Mann-Whitney U test, if your p-value is extremely low, then this tells you that it's actually very unlikely that your two samples came from the same population based on their rank, based on the ranked observations in your data. In the next module, we talked about chi-squared tests, which can be used to compare two distributions. Usually these are frequency distributions or proportions to each other. And we talked about how to calculate this manually how to calculate your chi-square statistic, your degrees of freedom associated with that test. And then we talked about using the chi-square test either as a hypothesis test or as a goodness of fit test. In Module 7, we began talking about analysis of variance, specifically a one-way ANOVA where we're focused on the effect of a single predictor on a continuous response. We talked about your sum of squares and how you can calculate the sum of squares between groups, within groups, and then from those calculate the within group and between group mean squared error. Ultimately, from those we calculate our F statistic, and then we compare that to the F distribution to arrive at a p-value for our ANOVA. Recall that for a one-way ANOVA, if we have a single predictor that only has two levels, okay, two groups, this is analogous to just a t-test. But the ANOVA is a little more flexible because we can also apply it when we have more than two groups, and we can also apply it when we have more than one predictor. To test the assumptions of ANOVA, we can use the Shapiro-Wilk test to assess the normality of our residuals, the Bartlett test to assess homogeneity of variance, so we want to make sure that the variance of all of our groups are approximately equivalent. Recall then that the p-value for our ANOVA tells us about whether one of the groups differ in terms of their mean from the other groups, but it doesn't tell us which pairwise contrasts are statistically significant. Okay, which group is different from the other groups, or are all the groups different from each other? So to get at that, we need to use our Tukey test. We look for pairwise comparisons between each of the groups in our one-way ANOVA, and this provides a little more detail about exactly which pairwise contrasts are statistically significant and which are not. In Module 8, we then moved from a one-way ANOVA to a two-way ANOVA, where we're interested in the effects of multiple predictors on our response. And so now we can begin to look at additive effects, where the predictors affect our response additively, or interactive effects, where the effect of one predictor depends on what level the other predictor is at. We talked very briefly about nested designs and random effects, where you have repeated measures on the same individual. Okay, so that assumption of independence of our points is sort of violated, and you can account for that using random effects. We talked about a few different ways that people sometimes set up their experiments in these factorial designs, fixed designs, randomized blocks. And then we talked about analysis of covariance. So this is formally where you're mixing ANOVA, where you're using categorical variables, with continuous predictors as well. Okay, and we can easily accommodate that in a linear model. And then we talked again very briefly about multivariate designs, MANOVA, but this is a topic that we would have to spend multiple weeks on, okay, just to scratch the surface of, so we didn't really focus on this too much in this course. At the end of the Module 8 lecture, I spent a little bit more time talking about how you can interpret p-values, and specifically about statistical versus biological significance. Effects can be statistically significant, but not really have much of a biological effect. And so you need to be interpreting both statistical significance, and then if it is statistically significant, is the effect size large enough for it to be biologically relevant? In Module 9, we moved on to simple linear regression, where now instead of a categorical predictor affecting our response, we have a continuous predictor affecting our response. We began by talking about correlation analysis, so how to assess the correlation between two continuous variables. And then at the end of the lecture, we moved on to formal linear regression, where now we're investigating the effect of our explanatory variable on our response. And usually we're hypothesizing some sort of causative effect there. So in our regressions, we then have an intercept, a slope, and some error associated with it. And we also get a p-value associated with that test. Okay, the p-value tells us whether the slope is significantly different from 0 or not. If the slope is equal to 0, that means that our predictor has no effect on the response. But if the slope is non-zero and it's significant, that means that as we change the values of our explanatory variable, our response then changes. So simple linear regression just deals with a single predictor, and then in Module 10 we moved on to multiple linear regression, where we're interested in the effects of multiple continuous predictors on our response. So multiple linear regression works much the same way as two-way ANOVA. Okay, and again, we actually discussed this a little bit in this lecture, but linear regression and ANOVA are closely related and are both fall under the category of general linear models. Okay, they're linear in the predictors. So when we begin to investigate the effect of multiple predictors on our response, we want to pay attention to a few different things. The first is we want to pay attention to the p-values associated with each of our coefficients. Okay, so do each of our predictors in our model have a significant effect on our response? We want to pay attention to the magnitude of those coefficients. That's the effect size. So how big of a change in the response do we actually see when we increase the value of our predictors? And then finally, we want to pay attention to the R-squared. This gives us a measure of goodness of fit of our regression, and it also tells us how much variance is actually being explained by our predictors. So if you have a very high R-squared, close to 1, that means that your predictors are doing a pretty good job of explaining all of the variation in your response. If your R-squared is very low, that means there's lots of unexplained variation. So there's lots of things that are affecting your response that are not being accounted for by your predictors. At the end of this lecture, we talked about model selection and AIC, and so how you can begin to compare the fit of models that include different predictors or different combinations of predictors. And finally, we finished off with model diagnostics, so assessing the assumptions of these models, which again assume normality of your residuals, homogeneity of variances, and independence of your observations. We then moved on to talking about a few different generalized linear models. So it turns out that the regressions we've been working with in previous weeks, okay, the ANOVAs, simple linear regressions, multiple linear regressions, are also generalized linear models. The link function that they use is the identity link, but if we have error terms that are non-normally distributed, then we can use other link functions to link our model coefficients to our non-normal response data. So the first generalized linear model we talked about was logistic regression. This is for binary response data. Okay, true, false, success, failure, live, dead, that sort of stuff. And we also talked about Poisson regression, where we can model count data. In this lecture, we talked about how to assess model fit and compare models to one another using information criteria. So these are based on maximum likelihood and deviance. And the information criteria that we focused on for the most part in this course is AIC, but there are other information criteria available as well. And in general, these just penalize model complexity a little bit differently than AIC. So it turns out that these other ones, BIC, or sometimes called SIC, Lee's talked about this a little bit in the lecture, they penalize model complexity more heavily than AIC. And some people feel that you should use one for one of these information criteria if you're mostly interested in testing hypotheses, and you should use another information criteria if you're mostly focused on model prediction. But they mostly just work the same way. The way you calculate them is just slightly different. And then at the end of the lecture, Lee's talked about forward, backward, and stepwise approaches to deciding which models to include in your AIC tables and how to eliminate models from your table sequentially. Some people prefer this approach to model selection. We didn't use that so much in this course, and we didn't use it very much in the labs at all. The philosophy that I've sort of been taught and I've been working with is that you should generally come up with all of the types of models you want to fit right from the beginning. Which ones make sense? Throw all of them into an AIC comparison table, and then choose the best one based on your a priori list of models that you created up front, rather than using forward, backward, and stepwise comparisons. But other people have a different philosophy, and so these are good things to know just in general when you start applying these methods to your own data. And Module 12 was focused on survival analysis. And so in this one, Lee's talked about the survival function, how that differs from the hazard function. Some other keywords that were focused on in that lecture were cumulative hazard, the probability density function. This should ring a bell from earlier in the semester, and your cumulative density function. We talked about two different sort of approaches to modeling survival. So you can use your non-parametric Kaplan-Meier estimator or your semi-parametric Cox proportional hazard models. And these can accommodate different sorts of predictors. We learned about how to interpret hazard ratios and what those really mean, and then the proportionality assumption associated with these models. And then at the very end of the lecture, Lee's talked about parametric, exponential, and Weibull models, but we didn't focus on that in the lab or the assignment. Module 13 was student choice, and in this week I posted a previous lecture that I had made for last year's class. It's an introduction to population viability analysis. In that lecture, we talked about what populations are, what stochasticity is, both demographic and environmental, population viability analysis and how it works. And then in the lab, we talked about how to use for loops to actually make some stochastic population projections and then generate some summary data. The information from this module was completely optional, and so this won't be on the final exam. But I do recommend you check it out. I just think it's kind of interesting stuff, and you might find some helpful tricks in the lab that you can apply to your own data later on. At the very least, just save the R code and use it later if you ever need to. So that wraps it up. That is a ton of information that we've covered in just a few short weeks. And it's kind of amazing to think back on how much stuff we've gone over. So over the course of this semester, we've learned how to write basic and some advanced programs in R, and how to comment them and make them easy to read and share with others. We learned how to manage, import, manipulate, export data, summarize and visualize data with a ton of different plots, develop ecological hypotheses, test those hypotheses with statistics, using a whole bunch of different tests and approaches, and then test the key assumptions for those approaches. And you've learned how to interpret and communicate results from these analyses and place them in appropriate biological context. So are they statistically significant? What's the effect size? What's the R squared? Is our model really doing a good job of predicting the response? Why or why not? Okay, and that's really at the heart of data analysis. Finally, what I hope you've learned from this class is enough of the basics of programming that you've built up a solid enough foundation that you can continue to search for your own programming and statistics help online. So you should be familiar enough with the terms and common functions and syntax that if you run into stumbling blocks when you're using this type of analysis on your own data, you should be able to Google it and interpret any help information you find online and then apply it to your own data, even with analyses that you've never encountered before. Okay, so finally, let's just talk about the final exam for a minute. So the final exam will be worth 30% of your final grade, and it will be available in Module 15. Okay, it'll be available from Monday, April 18th until Friday, April 29th at midnight. The exam is completely open book, so you can use any resources that you want online from previous lectures in this course, previous discussions. You can copy and paste material from the labs if you need to help address your questions, okay? But it is meant to be completed on your own. And so because of that, I'll be locking the discussion board as of April 18th. And if you have any questions about the exam, please email me directly and I'll try to respond as best I can. Now, I won't be giving you very much help about how to interpret any results of your analyses, but what I will be helping you with is if any of the questions are unclear and you're not quite sure what exactly the questions are asking, I can try to help interpret the questions. But I've tried to word them as carefully and clearly as I possibly can. So hopefully there shouldn't be too much misunderstanding in terms of what the questions themselves are asking. I've tried to make the exam as fair as possible, and hopefully it won't take you too much time, but it should serve as just a really helpful review of all of the skills that we've learned across the whole semester, and a nice chance to sort of demonstrate all the new skills that you've learned in the last couple months. Honestly, the final exam is best thought of as just a big assignment that you have just a little under 2 weeks to work on, and you'll actually submit the final exam through the assignments page on Canvas, just like you have been in all the previous weeks as well. So definitely don't leave it until last minute, because it is longer, much longer than any of the previous assignments you've worked on. I think there's 10 or 11 questions in the final exam right now. Some of them just require worded answers, other ones require R code, and some of them require both. So really pay attention to what the question is asking for, because if the questions are incomplete, I won't be able to give you full marks for them. But that's about it. It should hopefully be really straightforward. So again, I just want to thank everyone for taking the course and congratulate you on doing a great job. Everyone's done a really remarkable job and come a really, really long way in just a few short weeks. So it's really been my pleasure to teach this course, and I hope that you also had a good experience throughout the semester as well. So thanks again, congratulations, and good luck with the final exam.